Mindy and Kurt for the invitation to present alongside Emily, discussing one of many avenues to manage non-spatial data, spatialize the data, and then distribute that data across numerous platforms to drive business value. Specifically today, I will be addressing a particular product called SDE, which stands for Spatial Data Engine. This is an ESRI middleware solution to manage spatial data in a business context. It is a proprietary solution, and let's go ahead and jump in. So in light of a lot of data analytics and data availability, one of the most paramount things is having data available across multiple systems, which seems counterintuitive with a proprietary solution. A lot of software development companies historically in the past have kind of been black boxes. However, we find ESRI has become a solution, an enterprise solution, which is extendable and customizable and secure, and really lends itself to data availability and interoperability across multiple systems. So when addressing the question proprietary why, in light of a lot of FOSS 4G open source software solutions, the things that I kind of teased out, that we've kind of teased out, is this is an enterprise solution. It is vertically integrated, owned by ESRI, but there's been a tremendous amount of development across this solution that gives you the ability to kind of plug and play. It's an identity-based model that is incredibly secure, that ships with a bunch of IT best practices and protocols already built into a lot of the suites that are components of the whole enterprise solution. It's incredibly extendable. Customization and configuration never looks the same with a deployment. And with all the suite components, there's field applications, there's cloud applications, there's on-prem applications, and they're all interoperable across the whole entire platform. When you think about GIS in today's modern data kind of realm, the standards that ESRI has implemented and proselytized are industry-wide. ESRI has been adopted in the private sector and the public sector, from the DoD and the DOJ, county, small municipalities, oil and gas, education, you name it. So it's almost synonymous. ESRI and GIS are almost synonymous, but there are a ton of FOSS solutions that are really, really powerful as well. And the last thing is the support. Because this is such a big suite, ESRI has provided support that comes with maintenance and an enterprise license agreement that is available at your leisure. You just generate a case, you jump on a call. Sometimes it's fast, sometimes it's slow. They also have a professional business support team that can help customize and configure as necessary. To give you an idea of the way we're deploying spatial data internally, I wanted to give you a quick architecture schematic of our GIS system. So down at the very bottom, we have a centralized data warehouse, which has a SQL backbone. This is where we're streaming proprietary data streams and vendor data streams, all into a single clearinghouse. We're accessing that data in two VM boxes. The VM box on the left, I know it's a little hard to see, is our primary DevOps spatial box. This has ArcGIS Desktop, which is a 32-bit client, ArcGIS Pro, which is a 64-bit client. Both of those ship with Python 2x and 3x, can be used within those and outside of the software. We're leveraging the FME Desktop ESRI edition in order to drive the spatial DevOps functions. We have SQL Server Client. We're a big SQL shop. Task Scheduler to run the FME workbenches and the jobs that we create. And then Sublime Text is our primary text editor. On the other side, another VM box mirrors the VM box that we call our prod box. This is kind of more of our sandbox box, and it gives the GIS team the ability to stage stuff, build stuff before we push it to the prod box. In the center, you'll see SSMS. This is our SQL Server Management Studio. This is where SDE sits. As I mentioned, it is middleware, so it has a SQL backbone, and this is where our production and test databases reside. If you follow that up, we have a VM server. This is where we've deployed ArcGIS server. It's an on-prem behind the firewall server that we expose the spatial data. We have Portal for ArcGIS, which is an extendable kind of UI that gives us the ability to view and manage the services, the spatial data that we've published. We have a data store to manage a tile cache and a few other components. And then we have two web adapters. We have a server and a Portal web adapter that give us the ability to view that data in a slick UI. Going further on up, we have a GeoCortex cluster. This is a web-based HTML5 viewer that we're exposing a bunch of spatial REST endpoints and providing that as a corporate web map behind our firewall to all users of Centennial via Active Directory. So this gives you just kind of a nutshell. We plan on extending this quite a bit, so the architecture will look a lot different, but this is our current deployment. Our source data, as I mentioned, it's key to have a centralized data warehouse. That makes managing data so much better and so much easier. And then the different business analysts on our team are incredibly savvy and they know their data intimately. So in terms of spatializing data from a data warehouse, not only do we have it in a single location, we also have at our disposal a whole entire team with a depth of knowledge to help drive the end goal. As I mentioned, the SQL backbone plays really nicely, not only with ESRI's Arc SDE, which can sit on Oracle or SQL, our current deployment SQL. So it's pretty seamless for the GIS team or the DevOps spatial team and also our IT analytics team. I did mention that we're looking specifically at non-spatial data, even though I think we're all aware there is spatial data available in SQL Server these days, but I'm mostly just focusing for today's talk on the non-spatial component. For today's workflow, I wanted to quickly tease out some vendor data that we have. So this is our SQL Server data warehouse, and most of us are probably familiar with Drilling Info and IHS. Both of these are independent data sources, data vendors. And what we're working to do in this particular workflow is spatialize the master vendor header. So I'm not going to go into the nuances of creating this particular table, but essentially it's merging a master well header table. And there's a little bit of logic on the back end that if an API exists or a UWI exists in both of these, it's honoring one and ignoring the other, and then pulling and merging data together. So we have a golden record. Now within this table, there is no geometry column, but there is a latitude and a longitude for both surface and bottom. I've highlighted those in pink. We have a particular interest in pulling these particular data points into an FME workbench and spatializing the data from there. So our current spatial DevOps deployment has a few components. We're primarily using FME. If many of you are not familiar with FME, it is by Safe Software. They're based in Vancouver, Canada. It stands for Feature Manipulation Engine. This is an incredibly powerful tool, and it is incredibly affordable in terms of adopting and learning. The documentation and the support is quite substantial, and I believe you can have a license for under 2K and toss it into a production environment to help drive business value. We're also leveraging Python, as I mentioned, the 2x or the 3x line as necessary. FME does a lot of the work for you, but there's a Python caller. You could also do Python syntax and task scheduler to launch some of the FME jobs, and then kind of some one-off jobs that we're leveraging Python for. We are a huge SQL shop. Our team is super fluent with SQL, not only as the direct data warehouse, but also integrating SQL calls directly into FME. And then we're using Windows Task Scheduler to launch a bunch of the jobs in the workbenches that we're using to spatialize data and update and append and truncate on a regular basis. So we have the latest and greatest data from our vendor and proprietary data streams. So this is the primary component of our current spatial DevOps program. So I'm going to go ahead and jump right in to a pretty simple FME workbench. Please tell me when you can see FME workbench.
We can see it.
Okay, perfect. So there's three components. Let me see if I can move this. There's three components of FME that really make an FME workbench run. And I'm not going to get too deep into the weeds on this, but there's readers, writers, and transformers. Your readers are the source data that you're bringing into this workbench, this viewer UI here. You could connect to ASCII files, LAS files, Excel, SQL Server Spatial, SQL Server Non-Spatial. I mean, the list goes on. The writers are the intended output. After you use a whole bunch of functions, how you want the data delivered on the back end of your workbench. The transformers are the meat of the FME workbench. And there are a slew of transformers that I'd say this is probably the steepest learning curve, is understanding how these work and then being able to customize these based on your intended data manipulation, massaging, and output. So rather than using a reader, you can connect directly to a SQL table, SQL Server Spatial or SQL Server Non-Spatial with this reader. For this particular workflow, I'm actually using a SQL, which is a SQL caller directly back to the database. I'm going to go ahead and open this and quickly show you that Microsoft SQL Server Non-Spatial, the table we were interested in looking at, does not have a geometry column anywhere in here. So this is the SQL table, all the column elements, but we do see here that we have a latitude and a longitude in WGS 84 for both surface and bottom hole. For the sake of this workbench and the brevity of time, I'm only looking at Reeves and Pecos County in Texas. So I added that as a where clause in this. This does take a little bit to run, about 2 minutes. So I'm going to go ahead and run this while I continue talking. Let's jump back in here. I'm exposing all the attributes from that SQL call because I want them carried downstream and a component of the output. There's a few parameters that you can change in here. I'm not going to get into those, and I'm using an alias to our database. The attribute manager gives you the ability to customize very similar with an as clause in your SQL call. You can change the names of these. You could change the order of these. You can set a default value to pipe through, and so on and so forth within that transformer. Where the power of FME lies in terms of specializing the data is this little transformer here called a vertex creator. So I have two different data streams here. I have a vertex creator for surface hole location and a vertex creator for bottom hole location. If we open this up, we can see that I'm calling the latitude and longitude for the surface hole, and I'm replacing it with a point. So I'm creating a vertex with geometry in this and passing it downstream. Same thing with the bottom hole location. One thing I want to highlight is you see that we have a WGS 84 bookmark and a DBO just regular DBO schema owner. We're managing different coordinate systems in our SDE and in our SQL Server Management Studio by the use of schema owners. So our DBO by default is a NAD83 unprojected. We've also built a schema owner called WGS84, which manages that data coming from this reprojector engine in EPSG code 4326, which is WGS84. So we have surface hole and bottom hole dropping in NAD83 unprojected as well as WGS84. So as this continues to ride, I think it takes about 2 or 3 minutes. We can see on the output, we have the ability to set a geometry. So for these particular surface hole and bottom hole locations, we're using the point geometry. Now this already existed as a feature class in our SDE, and I'm just truncating a table based on that. So it already exists. I want to pull in new data, and this is where we'd use Task Scheduler to launch this job daily and just truncate what already existed in our database. You also have the ability to customize the field types. So date, varchar, double for precision, integers, date for a timestamp, so on and so forth. So now this just ran. It ran successfully. This log window is super, super helpful in terms of viewing where errors might occur as you're developing some of these transformers and these data streams within your FME workbench. We'll go ahead and minimize that. So I quickly wanted to show you where the data landed. We had it right to a SDE database, which is that middleware SQL Server that manages the geometry on behalf of SQL Server as it relates to ESRI's Enterprise Suite. So this is called Art Catalog. This is a component of the ESRI Suite. It is a viewer that gives you the ability, very much like SQL Server, to view the spatial data and the way you're currently managing it within your SDE. So we're looking at our GIS production database. I mentioned that we're using 2 different schema owners. We have a vendor data featured data set in DBO, which is a NAD83 unprojected, and the same with WGS84. Now, a feature data set is a container to hold multiple feature classes, points, lines, and polygons. The only caveat is they have to be in the same coordinate system to participate in a particular feature data set. Looking at the image in the middle, we can see all 4 of these feature classes landed where they were supposed to based on the way we configure that FME workbench. Now, if we were to right-click on any of these, this window on the far right would pop up, and this gives us the ability to look at the configuration we set up in the FME writer, how it looks when it lands in SDE. Of interest for this spatializing non-spatial data is this very last column. This is a shape column that has now been assigned geometry, point geometry. So now we can see we have point data based on non-spatial data in an SDE that is available to pipe into other data streams. Now I wanted to quickly showcase what the last slide looked like in SQL Server Management Studio. So this is the view from our catalog, proprietary viewer, and this is back in SQL Server Management Studio. So when we jump back into the GIS prod database, I only highlighted the 2 tables here. You can see that they're displaying, as you would expect, a table in SQL Server Management Studio, but of interest is now the geometry column that's assigned shape. The very bottom one, the GDB geometry attribute data, is specific to the SDE ESRI configuration. So now we have spatial data. The way we make this available is leveraging the rest of ESRI's suite. We're primarily consuming the spatial data from SDE in a 64-bit client called ArcPro. This is very similar to ArcMap. It's a little more ribbon-like, a little more fluent, easier to use, much quicker, and has some functionality to connect directly to portal and server. So it's a little more streamlined. So we're using ArcGIS Pro to publish data and services. And we're publishing those to our on-prem server, ArcGIS server, which is behind our firewall. And the server directly connects to our portal. Portal is a web-based UI that gives us the ability to look at the data in a fashion similar to ArcCatalog or SQL Server Management Studio, with additional extendability and functionality provided to us. So one thing to mention is Portal is RESTful. We have the ability to access a bunch of REST endpoints and use those map services or feature services and pipe them into numerous different software packages at our leisure. Right here on the left is the REST endpoint directory. You can see, because we've published with ArcPro the spatial data that we created, the master vendor, competitor, surface hole, and bottom hole locations. These are now accessible in our REST endpoint directory. So we can click on these, grab that REST endpoint, and put them in all sorts of web-based applications. Real quickly, I just wanted to give you a snapshot view of a geoprocessing tool that we're using to publish that data. So by pulling in the data into ArcPro, that's what we're looking at here, bringing in that spatialized data, and then symbolizing it, writing queries against it, SQL queries within here, we are able to name it, competitor surface hole location, tag it, expose it across the business, analyze it, and then publish. And that's when the record within the REST endpoint directory arrives. Everybody still with me? All right. This is a quick view of that same published data that you would see in the REST endpoint directory just within the portal UI. So this is a web-based viewer that gives you the ability to look at your services, and it also adds additional functionality to leverage Active Directory or portal ESRI identity store for managing groups and data availability. Within this platform, you also have the ability to build web apps and web maps. Web apps sit on top of web maps, and those are distributable within groups, and you can assign groups for particular Active Directory personnel. You can have a geology group, a reservoir group, so on and so forth, that have access to specific data and specific maps. So it adds quite a bit of behind the firewall mapping functionality within ESRI's suite just by itself. So we can see the competitor bottom hole and the competitor surface hole location within Portal. Again, with interoperability, by consuming those REST endpoints, we have extended the spatial data availability even beyond Portal. So we're currently leveraging a company called GeoCortex. Again, I think they're based out of Vancouver, British Columbia, and they have built a web-based mapping application. And this current deployment is an HTML5 viewer that our senior GIS analyst has done a tremendous job standing up, a gentleman named Thomas Douglas. Consuming those REST endpoints from our server that we've published through ArcPro and adding additional functionality and configuration within this viewer. And there's all sorts of tools. I accidentally snipped off the top, but there's panning, zooming, there's the ability to query and filter, So this particular view is that same spatial data that we'd published in a little tiny town called Orla, Texas, right off of 285, which its terminus is in Denver. So I thought that was pretty cool. And the population's only 2 in this little town. But we can see that when you click on a point, you can configure a pop-up that really helps expose some of the attribute data that would have been hidden in a non-spatial form. Extending it further, the reason why we're using that WGS84 schema owner is so the data can be piped in as an information link within Spotfire. So this again is that little tiny town Orla, same exact data set. You can do additional functionality, exposing with tooltips and pop-ups in the same fashion or capacity that we have in Portal, GeoCortex, and now in Spotfire. So it's essentially delivering the data in the preferred software of the audience. Extending interoperability more. In full disclosure, I haven't quite figured out how to get this to work, but I've successfully connected our ArcGIS portal, enterprise portal, to Kingdom, and you can see that we are now able to view all of the data that is being served out on our server through this connection in Spatial Explorer for Kingdom. And I'm able to add it. However, there's a little bit of a snafu, either a bug or a configuration parameter that still needs to be worked out. But this is incredibly hopeful that we're going to have the spatial data available in multiple end user applications. So more to come on this. And then lastly, kind of to wrap things up, the perspective that really drives this spatial solution across the business is the team I'm on. I'm incredibly honored to be on such a bright team. The people are incredibly driven, and they share information, and everyone has a slightly different perspective with technology. The technology available at our hands really helps streamline some of these solutions. And if one particular person on the team's not super fluent, help is, a team ping away. And it's the people and the technology that really helps drive the solution. So I hope you were able to pull a little bit away from this as one of many workflows to spatialize non-spatial data to drive business value. And that's all I have.
Great. I guess I can go ahead and take this from here. That was awesome, George. Thank you. So for those of you who don't know me, my name is Emily Huney. I work for High Point Resources. And let's see here. And I am trying to share my screen. Let's see here. Will you let me know when you guys can see it? Can you guys all see it?
Yep, we can see it.
Perfect. Okay. So, like I said, my name is Emily Huney. I'm a data scientist. I work for High Point Resources. And I actually, I have a really strong background in GIS. I used to work as a GIS specialist for about 6 years, primarily in the oil and gas space. And I'm here today, I'm going to take the second half of this presentation to talk to you all about the free and open source alternative to spatial relational database management systems. And specifically, I'm going to be talking about a program called PostGIS with a PostGIS extension. So I'm going to go ahead and start this. Before I actually dive into PostGIS itself, I do want to take a really quick step back and talk about why I like open source solutions to many of my projects. Now, I could probably talk about this particular topic indefinitely. However, I only have so much time. So I picked a few of my main points, and I'm going to just focus on those. So the first reason, which is probably the most obvious reason that I like open source, is because it's free. And because it's free, it's easily accessible to anyone who is interested in learning it. And I think this is actually a really incredible thing. I think this is incredibly empowering because I know for me personally, this has really allowed me to solve whatever data problems I have come up with basically my own solutions using open source softwares. It just takes a little bit of desire to learn and a little bit of creativity, and usually I can get to where I want to go using open source. The second reason why I like open source so much is because it tends to be very secure and very scalable. And so even though we don't really see it a ton in oil and gas, I will say that we actually, open source is actually very prevalent in other industries. In particular, we see it a lot in the tech industry. And finally, the final reason why I tend to really like open source options is because I find them to be incredibly robust in terms of functionality. So rarely can I not perform a task that I want to do when I'm using an open source solution. And the other thing that's really fun about this is because it's an open source solution, so it's created by an open source community, they're always adding on, they're always building out new open source programs or adding new features to existing open source programs. So those are some of the short reasons why I love open source. But I'm going to go ahead and dive into the actual program that we're here to talk about, which is PostGIS. So PostGIS is a free and open source relational database management system. And PostGIS is an extension to that, to PostGIS. And what it does is it turns it into a spatial relational database management system. So it does this by adding support for what are called geographic objects. So now I really, before I get too far into this, I really want to provide you all with some context in terms of how I use PostGIS in my day-to-day workflows. So I want to make it clear that I, as a data scientist, I don't have the responsibility of managing all the data for the company and getting it out to people. So I tend to use it in a different way. So primarily, my job involves aggregating a lot of different data from a lot of different data sources. Usually I have to do some sort of pre-processing using Python, but eventually I will get that data and I will want to upload it into a relational database environment. I do this for a few reasons. One, to just stay organized with my projects, but also because SQL databases are an ideal place for me to be manipulating my data, joining my tables, and doing any sort of analysis with my data sets. Now, because I'm working with a spatial relational database using PostGIS, I can include these spatial layers in this same type of workflow that I would include any other traditional data set that I was using to analyze. And the analysis portion of my job is important because eventually I create a data set in whatever format or including whatever analysis I find to be most interesting. And then I eventually incorporate this into larger data science models. But what I'm really trying to say here with this slide, and the big takeaway here, is that I come to this, I come from this from a perspective of being very analysis driven. And so most of this presentation is actually really going to be looking at how do we take spatial databases and use them to analyze our data. Okay, so with that in mind, this sort of analysis-centric viewpoint, let's go ahead and start talking about how spatial databases actually recognize tables as spatial. So George actually touched on this as well in his presentation. And basically spatial databases, SQL Server included, as well as PostGIS, they really need to have some sort of column that identifies them as being sort of a spatial layer. And so there are a few different geometry objects that exist that can do this, but the one that I like to work with and that I kind of get the feel is the most popular in terms of PostGIS, is what's called the geometry data type. So the geometry data type is really composed of three sort of fundamental concepts. The first one is it contains information about what type of feature you're working with in terms of what type of GIS feature. So are you dealing with a point or a line or a polygon or perhaps something else? And the second thing that the geometry column tends to, piece of information that it tends to contain is basically the projection information. So where it is in terms of a coordinate system. And then the third and final piece, and probably the most important piece, is these geometry columns for each feature within your data set. They basically contain the feature location and the feature shape. So you can see on my screen here, I have just a table kind of brought up that is looking at Petra well paths. And so we can see in one column, we have our APIs, and then in our next column, we have our geometry field. And this geometry field is basically drawing lines for each of these APIs. So it's basically drawing the line pathway for each of these well locations. So to kind of hammer this home, if you were to take this table, if you were to bring it into a GIS software, mapping software, such as QGIS, which is also a free and open source desktop mapping software. So if I were to take this table and just bring it into this map, you can see that these lines just draw automatically. And the way that they know to draw this way is through this geometry field. So now that we kind of understand this fundamental idea of what is a geometry field, we can start to get into what I consider to be the more exciting parts of spatial databases. And I would say that, and this is basically just the concept of spatial functions. So spatial functions are built into PostGIS. And they basically allow you to, you can wrap your geometry column in spatial functions and manipulate your geometry column either to do some geoprocessing or to analyze the geometry column or to manipulate it. And you can do all sorts of things using these spatial functions. So basically, the idea is that they serve as sort of a building block to any sort of spatial project that you have. But what's really cool about them is that you write them directly into your SQL code. So that being said, I wouldn't be surprised if I lost you guys a little bit. This was definitely a lot of jargon that I just threw at you in a very short period of time. And so I find the best way to understand the concept of geometry columns or the concept of spatial functions is just to see them in action. And so I'm going to do sort of a live demo that shows you guys how I like to utilize these spatial functions to do basic analysis. For my demo, I'm basically going to be looking at calculating 3D distances for offset well evaluations for the COGCC regulations. So the whole premise being that in a 3D space, we want to know how far apart each well line is before they're drilled. And we need to make sure that, that if they're too close together, that we're complying with COGCC regulations. So for this workflow, to give you guys a little bit of context before I jump in, I basically am using data that I downloaded for free from the COGCC. So it's just publicly available data. And the first table I downloaded is just a list of surface locations for wells in an area of interest. So it's about 70 wells, and it's just trying to cut down on the number of wells and just focus in on a specific area. And then for each of those wells, I basically scraped using Python a series of directional surveys. And then compiled each of those directional surveys into a single master CSV file that's very long and very narrow. For those of you who don't know, directional surveys are basically going point by point along the MD wellbore is basically mapping out the pathway of the wellbore in three-dimensional space. So I'm going to, similar to what George was doing, I'm going to spatialize both of these tables into a three-dimensional space. And then from there, I'm going to convert those points, those series of points, into lines. Now, finally, I'm going to take those lines and look at the neighboring lines to each of those lines and try and figure out what are the different distances between each of those lines. So basically just doing a distance calculation. So I'm going to go ahead and pull up QGIS now. I am going to do all of my work basically in a QGIS environment. However, I'm really just using QGIS to access the PostGIS data and the PostGIS SQL interface. So keep in mind that everything I'm doing for the most part is in PostGIS. Okay, so I have my map here of sort of the northern Colorado area. And I have my two data sets that I have gotten from the COGCC. So I'm just going to start by uploading these to my PostGIS database. I'm basically just dragging and dropping them in. And we can see that both went ahead and loaded correctly. So now I'm going to remove my layers that are just CSVs, and I'm going to want to work with my new tables that are actually inside my database. I'm going to start with my surface locations, and I'm basically just going to open up the SQL code in my DB Manager interface. And we can see here that when it just basically does a very simple select of this table. And then down below, it has all of the columns associated with the table. So we have our X and our Y data, we have an elevation column, and so on and so forth. So let's go ahead and spatialize this table. So we're going to start by creating a geometry field. But in order to do that, we need to utilize our first spatial function. So we're going to do st make point. And this takes two arguments, an X argument and a Y argument. And then if you have it, it can take an optional third point, which is the Z value. So we happen to have that information. And I'm going to alias this new column as geometry. So I'm going to hit execute. If I scroll to the end of my table, we can see now that we have a geometry field. Well, this is wonderful, but let's go ahead and update our original table with our new geometry field. So you can see now that our table is drawing as a point. It recognizes this as being a point, but it doesn't draw on our map. And the reason is because I have to go through a similar process to what George went through, which is setting some basic information that the program needs in order to recognize this and draw it in the correct location. So I'm going to utilize the spatial function st_set SRID. And I know that this data came in WGS 84. So the SRID equivalent is 4326. Now, before I even continue further, I'm actually just going to, I'm going to reproject this data actually. So I'm going to wrap my new geometry column in a reprojection transformation. So it's ST transform. And I'm going to reproject it into a projection that I know I want to work with, which basic units are feet. So I'm going to hit execute. I'm going to update my layer, and hopefully it's going to draw. Yes, it did. Excellent. So now we need to do the same thing, but with our bulk directional survey. So we're going to update our SQL query here. Now, to do this, we can see that we have our X and Y information, but it's in the form of an offset information, and we also have our TVD information. So I'm going to go into more detail on how to process that in a second, but let's at least start off with what we know. We know we want to turn this into a point. So let's do an st make points again. We know we're going to use our X offset in the X process. We know we're going to use our Y offsets in the processing of the data. And then finally, we know we're going to use our Z values are going to involve TBD. And we also know that this needs to be, the ESRI needs to be set for this. And this time we know it's going to be in a projection of 4413. Now I need to alias this as geometry. And let's go ahead and execute this. Okay, excellent. So we got our geometry field in here. But the thing is, if you work with directional surveys, you know that what I've done so far is kind of fundamentally flawed. And so that's because these are not true coordinates. These are offset from the surface location. So basically, that means we need to join our tables together in order to get that original surface location. So looking at my original query, rather than nesting that into my new query, I'm going to just save this query. I'm actually going to create a new view, and I'm going to call it the same name, but with GIS at the end. And let's go ahead and execute that and see if that shows up in our database. Oh, excellent. Okay. So we can see now that we have a points view that is a spatialized version of our surface locations. So now we want to go ahead and basically join this directional survey data to our surface locations. So we're going to alias our directional survey data to be table A, and then we're going to left join that to our new table. So our GIS enabled surface locations, and we're going to alias that as table B. So if I just join everything and bring all of the columns in, probably need an on statement. We need to know that the join fundamentally needs to know what to join on. And so these two tables need to be joined on the API, basically. Okay, excellent. So now we have all of our columns from all of our tables that are correctly joined. Now we don't actually really need that. We really just want the API values and the MD values for the most part, and then we're creating this geometry column. Those are really all we actually care about. So in order to finish completing this geometry column, we can now bring in our geometry information from table B. So I'm going to go ahead and say geometry information. I'm going to call it b.geometry because it's from table B. And we're going to wrap this in a spatial function that pulls out only the X information. So we're going to do st_x to just pull out that information. And then we're going to add our new X value from our original surface location to our offset values. Now, let's go ahead and do this equivalent thing for our Y value. So we're going to do sty on the surface location geometry, and we're going to add it to our offsets. And now finally, we need to do the same thing, but with our TBD values. So I'm going to go ahead and subtract the TBD values because rather than add, and so that's the big difference there. And the spatial algorithm for this is using st_z. Okay, so if I execute this, and then, oh, I forgot one last thing. So with all spatial layers, when you're working with spatial layers in a database environment within a GIS or within QGIS, it's going to need a unique identifier. And so I'm going to add a column that basically is just the unique identifier for this data set. Okay, so it's just row number. So now that that has been added, I'm going to go ahead and update my table, and hopefully my layers, yes, they drew. Excellent. So you can see here in a two-dimensional space, here is the pathway for each of my wells. And it's a series of points for each API, but it represents sort of the geographic pathway for each of these wells. I'm going to change the spatial representation real quick. Okay. And now to keep the code nice and clean, we're going to save this as a view. So create view. I want to save it as just a spatialized version of the previous table. Execute that, and let's see if it shows up in our database. Excellent. So now I have my spatialized version of my directional surveys. So now using this new table, I'm going to continue on by basically turning these points into lines. So let's start off by selecting from select star from this new table, which is called B. Yep, there we go. And I'm going to go ahead and execute. So it's the same thing that we had just seen in the previous spatialized window of the bulk survey data. And so what we want to do is just in kind of human English, what we want to do is for each API, we want to draw a line along the MDs for each geographic point. And so we're going to create a new geometry field. It's going to be very similar to what you've already seen. We're going to use the spatial function stMakeLine, and we're going to pull in our existing geometry field, and we're going to order by MD. And then we're going to call it as geometry. I'm going to alias it as geometry. And so the next step is going to be because we want to do this only, or we want to do this not as just one giant line, but as a series of lines within the database, we basically need to group each of these lines by API. So we have our API value, and we're going to group by API. So let's go ahead and execute this. Excellent. So for each API, we have a geometry. We need a unique identifier again. So row number over, let's add this on in. Okay, so now let's go ahead and create a new view so we can see whether or not our lines drew correctly. So I'm going to create view as, I think I'm going to call it directional survey producing lines. And so if I execute this, we can go back over to our database, refresh it, and we can pull in our new lines that were created and symbolize them differently. And we can see now that each of these lines follows these points. And so that's really great and all, but the truth is if we're doing distance calculations, we don't want to include these areas that are at the surface and really close together. So we actually need to update this view. I'm going to do a create or replace view. And we're going to basically make it so that we're only looking at non-shallow points. So we're going to add a where clause, where MD is greater than 5,000. Let's execute. And then if I zoom in, I'm going to take these points off. You can see now that the early parts of the well line have been cut off. It's still not great though, to be honest. I want it to be better. In particular, I'm looking at these areas, and that's not quite what I want. So I'm going to update this geometry field. I'm going to wrap it in another function that basically chops this line down by a percentage. So I'm going to do st line substring, and I'm going to chop this line down starting at 0.1%, going to 0.99%. And that looks like it's correct. Let's execute it and see what it does. So if I zoom in, excellent. Those little tails are gone, which is what I want. So my view has now been updated. So now I guess for the grand finale, I'm going to go ahead and take these lines from this directional survey producing lines view that I've created, and I'm going to do a self-join on them, basically. And I'm going to try and understand, basically, for each well, what are the neighbors around it and how close are those neighbors? So let's start by just bringing in my new table to this process. And we're going to, because it's a self-join, we're going to bring it in twice. And we're going to alias, the first one is A, and then we're going to alias the second one as B. Now this is an outer join, so we're going to do a where statement. And the really exciting thing is we're going to do an outer join based on the geometry column. It's going to be based on one of these spatial functions. So now we get to join our data based on these spatial functions. So we're going to use std within, which is basically just a search for any well within a certain distance of the well in question. So basically, we're going to take the geometries from both tables because we're comparing them against each other. And I'm going to do a search of 1,000 feet. And if I execute this, it did not work. I probably need a from statement. Okay, let's execute this. Okay, so we have table 1 and the geometries and table 2 and the geometries. And we know that all of these wells are within 1,000 feet of each other. But that doesn't actually really tell us that much. We really need to know what the actual distance is. So I'm going to bring in this spatial function st distance. And once again, compare the geometries between the two tables. And then we're going to call this new calculation distance between, execute you. Excellent. So now we have a distance calculation in feet between the two wells. So let's clean this up just a little bit more. I don't want them to join on where the APIs are the same. I want the APIs to be different. And then I also want to know what is the origin API and the to API basically. So it's to API. So I'm just kind of aliasing these columns, cleaning them up a little bit. So we can go ahead and see that this well over here is 132 feet from this other well. Now, in terms of analysis, this might just be enough information of what we want. But I always like to kind of check my work. I want to see it in a different platform, not just in a spreadsheet. And so I'm going to take this actually a step further, and I'm going to create a new geometry field that basically makes a line between the closest points between the neighboring wells. And so I'm actually just going to copy and paste this in because I think I'm running short on time. But basically, it's the same functions that we've seen before. We have the st make line, and then we are also comparing the geometries for the st closest point for the start well, and then the closest point for the neighboring well. So if I hit execute, I probably need to, I did not put this in the right place, excuse me. This is the danger of copy and paste. Okay, comma, and let's see if this works. Okay, so now we have a new geometry line. So finally, I'm going to go ahead and save this as my final view. I'm going to call it basically just distance measurements between lines. And I'm going to hit execute. And let's see if this shows up. Yes, it does. Excellent. So I'm going to pull it into my map. You know what? It didn't draw. And you know why? Because I did not add a unique identifier. So really quickly, I'm going to do that. I'm going to do the row number one. I'm going to execute you. Interesting. Maybe it did work and I just need to pull it in. Okay, yes, it did work. Excellent. So here are the lines between each neighboring well that are of interest. So we can see here, if we zoom on in, we can see here are the lines between them. And if we want to take this a step further, we can identify these and take a look at the actual distance calculation. So we can see here these two wells are separated by about 940 feet. So what's really wonderful about this process, I'm just going to wrap this up real quick. What's really wonderful about this process is that these SQL calls are now stored in our database. And so if the underlying data were to change, these views actually will change with it. And so I just really quickly want to show you what that potentially can look like. And you're going to want to look kind of in this area over here. Now, I have here just a basic, I'm just using Python to update my table and append new data to it. So I'm just going to hit run all. Excellent. And if I change the view, now I have new lines and I have new distance calculations for my new wells. So basically, I'm kind of running up on my time limit, but this really concludes sort of the demo, but also my part of the presentation. If there's one message I hope you guys take away from this presentation, it's that GIS layers have a lot of potential, both for analysis and for visualization processes. And what's really important here, no matter what tool you use, is that you're manipulating and using these GIS layers to their full potential, ideally in an automated fashion, because there's a lot of tools out there for you to do that in, and it really can tap into the full potential of your GIS layers. So I'd say with that, I think I'm done. I think we can go ahead and open this up for questions.
Great. Thank you both very much. That was great. As Emily mentioned, does anybody have any questions for either George or Emily? We'll go ahead and ask. Oh, sorry. Go ahead.
I was just saying, great job, Emily.
Oh. I'm going to ask about data governance and if there's, between both platforms, any suggestions you have around governance, which program that takes place in, et cetera.
I'll chime in on the kind of ESRI suite side in terms of data governance. Deploying a system like this requires multiple people and multiple hats on the infrastructure side, on the DB side, and then also in terms of stewardship. So data governance, really identifying the different teams responsible to steward the data that they manage, that they want distributed throughout multiple packages, is key to success. If that stewardship and that governance solely resides on a GIS team or an analytics team, it can quickly muddy the water and the buck can get passed and data quality is compromised. So that's kind of from our perspective.
And to kind of echo what George is saying, I totally agree. I think it's such an important part of being able to have a single source of truth for your databases and making sure that everyone in a company is in fact working off the same information. I have to actually go ahead and say that my the GIS team at our company, although I'm no longer on it, they're just wonderful, and they actually have a very similar type architecture to some of the architecture that you guys were talking about, and they definitely are stewards of this data, and they take it very seriously, and they make sure that anything that they put out there in terms of layers that I potentially need, they make sure it's correct and that there are certain workflows in place to make sure that the single source of truth is maintained.
First off, nice job. The question I have is for Emily. What kind of, like how many wells have you pushed that workflow to, and what kind of speed do you get on those?
So I've done it for the entire COGCC data, all the wells in the DJ basically. And my big piece of advice is if you're interested in doing that, views are notoriously will become very slow once you have a big GIS data set. And so the trick at that point is to put it into a materialized view. And so at that point, that has basically an automatic trigger that updates those data, those materialized views whenever the underlying data is updated. So materialized views allow you to index, and they can potentially, that's the best way around that. So.
Cool, thanks.
Now that you're merging all of this spatial and non-spatial data kind of into one platform, have either of you noticed any like discoveries that you've made, like new workflows or business improvements that have really jumped out that we could maybe take to our use cases?
I guess one of the projects that I don't know how much I can talk about it, but I think this sort of fundamental concept of where are things located near each other, so distance calculations can be incorporated into really cool questions of larger questions. And so on a high level, I'll say that we are working on, for instance, depletion metrics. So like how much depletion are you seeing based on in an area based on how many walls are located there. So.
Yeah, kind of echo that. I think the major takeaway is the spatial perspective across the business differs. So a reservoir engineer is going to look at spatial relations slightly different than a drilling engineer versus a geophysicist. So my major takeaway, and something I'm guilty of sometimes, is making sure you have the right people in the room when you're developing these projects, because a GIS-centric perspective is not necessarily the solution in displaying, building, and disseminating spatial data. So this perspective across multiple teams really helps galvanize the final solution. So that would probably be my major takeaway.
Perfect. Thank you. Does anybody else have any questions? Perfect. All right. Before we jump off, Zach, I think you're on the call. There's a meeting tomorrow. It's a different group, kind of around Power BI, and getting kind of a user group around Power BI. Zach, do you want to talk about that real quick?
Sure, yeah, there's a group of us that have gradually been trending towards using the Power Platform, both for Power BI as an analytics tool, as well as Power Apps for kind of a low-code, no-code development. So I just put a link to that meetup is tomorrow morning on Microsoft Teams. You've got to register through Meetup to get the link. We've got over 100 people signed up for that, so that's pretty exciting. We'll be going through some dashboarding that we've been doing just for kind of company-wide metrics, both on laptops and smartphones and all kinds of destinations. Next month, Mike Party and Sean Bruce from Hess are going to talk about a Power App that they built. So come check it out. It's a little more application specific than this group, obviously, but probably a lot of overlap and interest between the two. Thanks.
Agreed. Looking forward to it. Perfect. All right. Well, Emily, George, thank you very much. That was great. If anyone has any follow-up questions for them, feel free to email me, or if you have their emails, reach out. Thank you all for joining, and have a great rest of your day.
Great.